Welcome! In this session, we'll tackle LeetCode problem number 1187, make array strictly increasing. This problem challenges us to transform an array into a strictly increasing sequence with minimal operations. Stick around as we explore the optimal approach to solve it step by step. In this problem, we have two integer arrays, arr1 and arr2. The task is to determine the minimum number of operations required to make arr1 strictly increasing. An operation is defined as replacing any element in arr1 with any element from arr2. If it is not possible to make arr1 strictly increasing, the function should return -1. Remember, an array is considered strictly increasing if each element is smaller than the one that follows it. The input consists of two arrays, arr1 with a length between 1 and 200, and arr2 with a length in the same range. The output is an integer representing the minimum number of operations, or -1 if it's impossible to achieve the goal. Here's the first example to illustrate the problem. Consider arr1 equals 1, 5, 3, 6, 7, and arr2 equals 1, 3, 2, 4. The output is 1. To make arr1 strictly increasing, we can replace the element 5 in arr1 with 4 from arr2. This results in arr1 equals 1, 4, 3, 6, 7, which is now strictly increasing. Notice that only one operation is required to achieve this result. Now, let's look at another example. For arr1 equals 1, 5, 3, 6, 7, and arr2 equals 4, 3, 1, the output is 2. In this case, we need two operations to make arr1 strictly increasing. First, we replace 5 in arr1 with 4, and then replace 3 with 6. The resulting array is arr1 equals 1, 4, 6, 6, 7, which satisfies the strictly increasing condition. A total of two operations were required. On the other hand, in a third example with arr1 equals 1, 5, 3, 6, 7, and arr2 equals 1, 2, 3, 4, the output is -1 because it is not possible to make arr1 strictly increasing using the elements in arr2. Finally, let's review the constraints and edge cases for this problem. The lengths of both arr1 and arr2 are between 1 and 200, and their elements can range from 0 to 10 to the power of 9. Additionally, all elements in arr2 are distinct, but arr1 and arr2 may contain duplicates. For edge cases, note that if arr1 is already strictly increasing, the output should be 0, as no operations are needed. Similarly, if arr2 contains only values smaller than all elements in arr1, it may be impossible to create a strictly increasing sequence, resulting in an output of -1. For very large values in the arrays, the solution logic should remain unaffected. Finally, when arr1 contains only one element, it is always strictly increasing, so the output in such cases will always be 0. To solve the problem of making arr1 strictly increasing with the minimum number of operations, we need to carefully balance correctness and efficiency. Let's consider a few approaches. The first is the brute force approach. Here, the idea is to replace each element of arr1 with all possible values from arr2 and recursively evaluate every combination to determine the minimum operations. While this ensures all possibilities are explored, it has exponential time complexity due to the sheer number of combinations, making it computationally infeasible for larger input sizes. The second approach, and the one we ultimately choose, is dynamic programming with state tracking. This method focuses on efficiently tracking the minimum operations required to make the first I elements of arr1 strictly increasing. A key insight here is that each element in the sequence must be greater than its predecessor. By sorting arr2, we can use binary search to quickly find valid replacement values for arr1. This approach balances correctness with computational efficiency, making it suitable for larger inputs. Now, let's dive deeper into the dynamic programming approach. For each element in arr1, we have two options: either keep it as is, provided it's greater than the previous element, or replace it with the smallest valid value from arr2 using binary search. The base case starts with no elements processed and 0 operations. This ensures that our state transitions build up from a clear foundation. The overall complexity of this method is n*m*log m, where n is the size of arr1 and m is the size of arr2. The binary search within arr2 ensures that replacements are efficient. This makes the approach well suited for competitive programming scenarios involving larger input sizes. While the greedy approach might seem appealing, as it replaces elements with the smallest possible values to maintain monotonicity, it can fail in edge cases where a local replacement leads to future conflicts. This is why we prioritize the dynamic programming approach, which ensures both correctness and efficiency. Dynamic programming is the chosen strategy for several reasons. First, it's efficient. Using binary search within ARR2 ensures the solution is computationally feasible, even for larger inputs. Second, it's complete. Unlike greedy methods that risk missing the optimal solution, the DP approach systematically evaluates all possibilities to guarantee correctness. Third, it scales well with input size due to its state tracking mechanism, making it an excellent choice for competitive programming. Of course, there are trade-offs. The DP approach requires additional memory to store intermediate states, but this is a manageable cost given the constraints. Sorting ARR2 incurs an upfront cost of O(m*log m), but this is negligible compared to the exponential complexity of brute force methods. In conclusion, the dynamic programming approach, combined with binary search, offers the best balance of efficiency and correctness, making it the most robust solution to this problem. In this problem, we're tasked with making an array, RR1, strictly increasing by replacing some of its elements with values from another array, RR2. The catch is that each element of ARR2 can only be used once, and any replacements must maintain strict monotonicity. To solve this, we start by pre-processing ARR2. Specifically, we sort it and remove duplicates. This step is crucial because it allows us to efficiently search for valid replacements later using binary search. Sorting ensures that we can quickly find the smallest element in ARR2 that satisfies the conditions for replacement. The time complexity of this step is O(m*log m), where m is the length of ARR2. Next, we define our dynamic programming state. The state dp, I, previous, represents the minimum number of operations needed to make the first I elements of ARR1 strictly increasing, given that the last chosen element is previous. This state captures two important details: how many elements we've processed and the constraint of strict monotonicity. To optimize memory usage, we use a dictionary to store only the relevant states, which helps avoid redundant computations. We begin our algorithm with the base case. At the start, no elements of ARR1 have been processed, and no operations are needed. So, we initialize dp 0 minus 1 equals 0, where minus 1 serves as a placeholder for no prior element. From there, we iterate over each element of ARR1. For every index I, we process all possible previous values stored in dp I. At this step, we have two options for each ARR1 I. The first option is to keep ARR1 I as is. If ARR1 I is greater than previous, we update dp I plus 1 ARR1 I with the minimum operations needed for this state. The second option is to replace ARR1 I with an element from ARR2. Using binary search on the sorted ARR2, we find the smallest element greater than previous. If such an element exists, we update dp I plus 1 replacement with the current operations plus 1. The time complexity of this process is O(n*k*log m, where n is the length of ARR1, k is the average number of states in dp, and m is the length of ARR2. After processing all elements, we extract the result by finding the minimum value in dp, n. If no valid state exists, we return -1. The efficiency of this algorithm hinges on several key insights. First, binary search on the sorted ARR2 allows us to quickly find valid replacements, significantly reducing the complexity compared to a linear search. This optimization is made possible by the pre-processing step where we sort ARR2. Second, state compression is achieved by using a dictionary to store only the relevant dp states. This avoids the memory overhead of maintaining a full 2D table, especially since many states may be irrelevant or redundant. Finally, strict monotonicity is enforced by tracking the previous state and ensuring that any replacement from ARR2 is strictly greater than the previous element. These components work together to guarantee that the resulting array is strictly increasing while optimizing both time and space. For data structures, we rely on a dictionary for dynamic programming, which dynamically stores states as needed. Additionally, the sorted list of ARR2 provides the foundation for efficient binary search when selecting replacements. When tackling this problem, it's important to account for edge cases. One such case is when no valid replacement exists in ARR2 that satisfies the monotonicity condition. In this scenario, the algorithm should return -1. Another case occurs when ARR1 is already strictly increasing. Here, no replacements are necessary, and the result should be 0. Additionally, for single-element arrays, either in ARR1 or ARR2, the solution must handle these trivial cases appropriately. From a complexity standpoint, the time complexity of the algorithm is O, n asterisk k asterisk log m, where n is the length of ARR1, k is the average number of states per index in DP, and m is the length of ARR2. The space complexity is O, n asterisk k, as it depends on the compressed DP dictionary that stores relevant states. Together, these considerations ensure that the algorithm is both efficient and robust for handling various input scenarios. This solution to LeetCode problem number 1187, make array strictly increasing, uses a dynamic programming approach combined with binary search to efficiently determine the minimum number of replacements needed to make ARR1 strictly increasing. Explanation. 1. Sort and deduplicate ARR2. Since elements of ARR2 will be used for replacements, we sort and remove duplicates to simplify binary search operations. 2. Dynamic programming initialization. We use a dictionary DP where keys represent the last element of the strictly increasing sequence up to a certain point, and values represent the minimum number of operations required to achieve that sequence. Initially, the dictionary is -1, 0, meaning no operations have been performed, and the last element is effectively smaller than any possible value in ARR1 or ARR2. 3. Iterate over ARR1. For each element of ARR1, we create a temporary dictionary temp to store the next state of DP after processing the current element. 4. 2 choices for each element. Keep the current element. If ARR1 I is greater than the previous element, previous, we add it to temp with the same number of operations as the current state. Replace with an element from ARR2, using binary search, bisect_right, we find the smallest element in ARR2 that is greater than previous. If such an element exists, we update temp with one additional operation. 5. Update DP. After processing all options for ARR1 I, we replace DP with temp, effectively moving to the next state. 6. Result. After processing all elements of ARR1, the minimum value in DP represents the minimum operations required. If DP is empty, it means no valid sequence could be formed, and we return -1. Complexity. Time complexity. Sorting ARR2 takes O, m asterisk log m, where m is the size of ARR2. For each element of ARR1, we perform a binary search on ARR2, leading to a total complexity of O, n asterisk log m, where n is the size of ARR1. Space complexity. The dictionary DP can hold at most O, n states, leading to an O, n space complexity. This approach ensures an optimal solution by exploring all possible sequences while efficiently pruning invalid or suboptimal paths. Here, we start by importing the necessary packages and defining our solution class with the method makeArrayIncreasing. The goal of this method is to determine the minimum number of operations required to make the array ARR1 strictly increasing, where an operation involves replacing an element in ARR1 with one from ARR2. First, we use a tree set to store all unique elements from ARR2, which allows us to efficiently find the smallest element greater than a given value. Next, we initialize a variable n to store the length of ARR1 and a dynamic programming map DP to track the minimum operations required to achieve a strictly increasing array up to each value. The map starts with a base case where the key is -1, representing a hypothetical previous value smaller than any possible array element, and the value is 0, indicating no operations have been performed yet. We then enter a loop over the indices of ARR1, where for each index, we prepare a temporary map temp to store the updated state after considering the current element. Within this loop, for each entry in the current DP map, we evaluate two options. First, we check if the current element ARR1 I can be kept as is while maintaining the increasing order. If so, we update temp with the current value of ARR1 I and the corresponding operation count. Next, we consider replacing ARR1 I with the smallest value in ARR2 that is strictly greater than the previous value. Using the higher method of treeset, we efficiently find this next greater value. If such a replacement is possible, we update temp with the replacement value and increment the operation count by 1. Once all entries have been processed, we update DP to the newly computed temp map for the next iteration. After the loop, we check if the DP map is empty, indicating that it was impossible to make the array strictly increasing. If not, we return the minimum value in the map, which represents the least number of operations needed. This completes the implementation of the method. To solve the problem, let's start with the first example where ARR1 is 1, 5, 3, and ARR2 is 1, 2, 3, 6. The first step is pre-processing ARR2 by sorting and removing duplicates, which gives us 1, 2, 3, 6. We also initialize a dynamic programming map, DP, with a key of -1 and a value of 0. This represents the previous element and the minimum number of operations needed so far. Now, in the first iteration, we are looking at ARR1, 0, which is 1. The current DP state is -1, 0. We check if we can keep this value, and since 1 is greater than -1, we update a temporary map temp to 1 o'clock, meaning no operations are needed. Next, we consider replacing ARR1, 0. Using binary search with bisect_right, we find the smallest value in ARR2 greater than -1, which is ARR2, 0, or 1. Replacing doesn't change the temporary map, so temp remains 1 o'clock. Finally, we update DP to 1 o'clock. Now, for the second iteration, we consider ARR1, 1, which is 5. At this point, the current DP state is 1 o'clock. First, we check if we can keep 5. Since it's greater than the previous value, 1, we update temp to 5 o'clock, meaning no operations are needed. Next, we consider replacing 5. Using bisect_right, we find the smallest value in ARR2 greater than 1, which is ARR2, 1, or 2. Replacing ARR1, 1, with 2 requires 1 operation, so we update temp to 5 o'clock, 2, 1. After finishing this step, we update DP to 5 o'clock, 2, 1. For the third iteration, we now look at ARR1, 2, which is 3. The current DP is 5 o'clock, 2, 1. For the previous value of 5, keeping 3 is not possible because 3 is not greater than 5. However, for the previous value of 2, we can replace 3 with the next valid value in ARR2, which is ARR2, 3, or 6. This requires 1 additional operation, so temp becomes 6, 2. We then update DP to 6, 2. Finally, the minimum value in DP is 2, which means the minimum number of operations required is 2. So, the result is 2. Let's move on to another example where ARR1 is 1, 3, 2, and ARR2 is 4, 6, 8. After pre-processing ARR2, we get 4, 6, 8, and we initialize DP as -1, 0. In the first iteration, we consider ARR1, 0, which is 1. The current DP is -1, 0. Checking if we can keep 1, we see that it's greater than -1, so we update temp to 1 o'clock, with no operations required. Next, we consider replacing 1 with the smallest value in ARR2 greater than -1, which is ARR2, 0, or 4. This replacement requires 1 operation, so temp becomes 1 o'clock, 4, 1. After this iteration, we update DP to 1 o'clock, 4, 1. In the second iteration, we look at ARR1, 1, which is 3. The current DP is 1 o'clock, 4, 1. For the previous value of 1, we can keep 3 because it's greater, so temp becomes 3 o'clock. Replacing 3 with the smallest value in ARR2 greater than 1, which is ARR2, 0, or 4, requires 1 operation, so we update temp to 3 o'clock, 4, 1. For the previous value of 4, keeping 3 is not possible as 3 is not greater than 4. However, replacing 3 with the next valid value in ARR2, which is ARR2, 1, or 6, requires 1 additional operation. This updates temp to 3 o'clock, 4, 1, 6, 2. Finally, we update DP to 3 o'clock, 4, 1, 6, 2. In the third iteration, we consider ARR1, 2, which is 2. The current DP is 3 o'clock, 4, 1, 6, 2. For the previous value of 3, keeping 2 is not possible as it's not greater. Replacing 2 with the smallest value in ARR2 greater than 3, which is ARR2, 0, or 4, requires one operation, so temp becomes 4, 1. For the previous values of 4 and 6, replacing with ARR2, 1, or 6 keeps the operations unchanged, updating temp to 4, 1, 6, 2. After this iteration, we update DP to 4, 1, 6, 2. The minimum value in DP is 1, so the result is 1. In the next example, we have ARR1 as 5, 4, 3, and ARR2 as 1, 2, 3. After pre-processing ARR2, we get 1, 2, 3, and DP is initialized to -1, 0. For the first iteration, we consider ARR1, 0, which is 5. The current DP is -1, 0. Since 5 is greater than -1, we can keep it, so we update temp to 5 o'clock. Replacing 5 with the smallest value in ARR2 greater than -1, which is ARR2, 0, or 1, requires one operation, so temp becomes 5 o'clock, 1, 1. After this step, we update DP to 5 o'clock, 1, 1. For the second iteration, we consider ARR1, 1, which is 4. The current DP is 5 o'clock, 1, 1. For the previous value of 5, keeping 4 is not possible as it's not greater. Replacing 4 with the smallest value in ARR2 greater than 5 is also not possible, so we move to the next previous value, 1. Replacing 4 with the next valid value in ARR2, which is ARR2, 1, or 2, requires one additional operation, so temp becomes 1, 1, 2, 2. After this step, we update DP to 1, 1, 2, 2. Finally, for ARR1, 2, which is 3, the current DP is 1, 1, 2, 2. For the previous value of 1, keeping 3 is possible as it's greater, so temp becomes 3, 1. For the previous value of 2, replacing 3 with ARR2, 1, or 3 requires no additional operations, so temp remains 3, 1. After this iteration, DP becomes 3, 1. The minimum value in DP is 1, so the result is 1. To analyze the time complexity of this solution, we start with sorting and deduplicating the second array, ARR2. This operation takes m asterisk log m time, where m is the size of ARR2. Next, we have the outer loop, which iterates over each element of ARR1. Since ARR1 has n elements, this loop runs n times. Inside the outer loop, there is another loop that iterates over the keys in the dynamic programming dictionary DP. The size of DP is bounded by the unique values from both ARR1 and ARR2, giving it a maximum size of n plus m. Additionally, within the inner loop, we use the bisect_right function to perform a binary search on ARR2. This binary search is efficient and takes log m time. Together, these steps form the building blocks of our time complexity analysis. When we combine all these components, we can calculate the total time complexity. Sorting ARR2 contributes m asterisk log m. The outer loop takes n, and the inner loop iterates over up to n plus m elements. For each iteration of the inner loop, we perform a binary search, which takes log m. Multiplying these factors together, we get a total time complexity of m asterisk log m for sorting, plus n asterisk n plus m asterisk log m for the nested loops. Simplifying this, the overall time complexity in the worst case becomes n asterisk m asterisk log m. This is a significant improvement over a brute force approach, as we'll discuss shortly. The space complexity of the solution is determined by the storage requirements of various components. First, after deduplication and sorting, ARR2 takes m space. Next, we have the dynamic programming dictionary DP, which stores the valid states of the computation. The size of DP is bounded by the number of unique values that can serve as the previous value in an increasing subsequence, which is at most n plus m. Additionally, at each step, we create a temporary dictionary temp, which has similar size constraints as DP. Since these dictionaries are reused and their sizes do not grow beyond n plus m, the total space complexity of our solution is n plus m in the worst case. To put this into perspective, let's compare this optimized approach to a brute force solution. A naive method would involve trying all possible combinations of replacements for ARR1 using elements from ARR2, ensuring the resulting array is strictly increasing. This would require recursively exploring all combinations, leading to an exponential time complexity of O2 to the power of n, which becomes infeasible for large inputs. In contrast, the current solution optimizes the problem using dynamic programming and binary search. By maintaining only valid states in DP and efficiently selecting replacements with binary search, the complexity is reduced to O(n*m*log em. In terms of best, average, and worst cases, the algorithm performs as follows. In the best case, if ARR1 is already strictly increasing, the time complexity reduces to O(n**log m as only binary searches are performed. In the average case, the complexity remains O(n**m*log m as most elements require examination and potential replacement. Even in the worst case, where all elements of ARR1 need replacement and DP approaches its upper size limit, the complexity still holds at O(n**m*log m. This robustness makes the optimized approach far more practical for real-world scenarios. Here, we highlight some common mistakes to avoid when solving this problem. First, not sorting ARR2 before performing binary search can make your solution inefficient or incorrect. Since ARR2 is the pool of replacement values, sorting it ensures you can quickly find the smallest valid replacement for any given element in ARR1. Next, overlooking duplicate values in ARR2 can lead to redundant operations or incorrect replacements. Deduplicating ARR2 ensures that each replacement value is unique and simplifies the logic. Skipping edge cases is another frequent pitfall. For example, you should test situations where ARR1 is already strictly increasing, or when either array is empty, as these scenarios can expose hidden issues in your solution. Additionally, relying solely on a greedy replacement strategy without dynamic programming is problematic. Greedy methods often fail to account for future constraints, while DP allows you to track all valid states comprehensively. Lastly, inefficient state representation in your DP approach can significantly increase runtime. For instance, tracking all indices or failing to prune invalid states leads to exponential complexity. Instead, use efficient states like index, previous_value, to optimize performance. Now, let's explore some insights that are particularly useful for interviews. This problem is a hybrid of dynamic programming and binary search, so it tests your ability to combine these techniques effectively. Interviewers often look for how well you can identify these components in the problem and implement them. Recognizing patterns is also critical. Many problems involving strictly increasing sequences require tracking valid states based on previous elements, and this one is no different. While greedy approaches may seem appealing, you need to explain why they fail and how dynamic programming ensures correctness. Additionally, interviewers value discussions about optimization trade-offs. Sorting ARR2 initially, for example, has a time complexity of O(n*log n, but it simplifies the replacement process during the DP calculation, making your solution more efficient overall. Finally, drawing connections to related problems can showcase your broader understanding. For instance, problems like LeetCode 300, which focuses on the longest increasing subsequence, or LeetCode 1035, which involves DP with replacement strategies, are directly relevant and help build the foundation for solving this challenge. Finally, let's consider some alternative approaches and their trade-offs. A brute force method would involve trying all possible replacements in ARR1, leading to an exponential time complexity of O(n**2 to the power of m. While this is infeasible for large inputs, it can be useful to validate your solution on small test cases. A greedy approach, where you replace each element in ARR1 with the smallest possible value from ARR2 to maintain a strictly increasing sequence, is faster but often fails because it doesn't account for future constraints. The optimal strategy combines dynamic programming with binary search. Here, DP is used to track the minimum operations needed to make ARR1 strictly increasing up to a given index, and binary search helps efficiently find valid replacements in ARR2. This approach balances correctness and efficiency, achieving a time complexity of O(n**m*log m. By understanding these trade-offs, you can better tailor your solution to meet both performance requirements and problem constraints. Great job! Today, we explored a dynamic programming and binary search-based solution to make array strictly increasing. Remember, mastering these techniques is key to solving similar optimization problems. Thanks for tuning in. Don't forget to like, share, and subscribe for more insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!